Hello, a very warm welcome again to Skeptics in the Pub online. I'm Cleo from Hampshire Skeptics. I've been hosting the Winchester Skeptics in the Pub for the last few years. We have a wide variety of speakers, both locally and here online, and they all approach their different subjects from a rational, evidence-based point of view. But we know that our rationality is totally hamstrung if it doesn't informed and is informed by our emotions. And it's hard to imagine a worse week emotionally than this last one has been, as we've all been watching the horror that's happening in America. We've decided, therefore, to divert all our takings from PayPal this week to UK Black Lives Matter. They've been in existence since about 2016, and they have a fundraiser on GoFundMe. So we chose this because although we're watching all the horror in America at the moment, here in the UK, we're really far from free of institutional racism. An example close to my own heart currently as a medic is the differential death rate from COVID-19, with Black, Asian and ethnic minority staff dying disproportionately. The government recently withheld their report, and then they published it quietly this week, noting the different death rates, but leaving out the chapter with contributions from thousands of relevant organisations, such as the Muslim Council of Great Britain. So there was no commentary on it at all. I'm part of an organisation called Every Doctor, whose inquiries lead us to be pretty certain that the probable cause of the excess deaths in these BAME staff are due to differential access to PPE. Their requests are much more likely to be denied. My fear is that without this information, there are going to be plenty who are going to jump on the genetics bandwagon, which will be both wrong and dangerous. Institutional racism, even when it's unconscious, kills. Fortuitously, in 2 weeks' time, we have a talk from Angela Saini talking about the worrying re-emergence of race science. So that is actually pretty timely. So please, can I ask you all to be generous in your PayPal donations this week? Every penny we get will be donated to the UK Black Lives Matter fundraiser. In addition, the skeptics organisations around the UK have been really generous. The online one and Merseyside are offering to match any donations up to £500. And there are a number who've also offered to match up to £200. I know Newcastle and Hampshire. There may be more who've been commenting in the chat, and I'm afraid I've not seen them yet. So I do apologise to those groups. But so that's up to, I think, 6 times, somebody said, up to the first £200. Moving on to tonight, we're going to hear something which for many of us is actually very much needed, pure escapism, cosmology. Our speaker tonight is Professor Karen Masters. She's a professor of astronomy and physics at Haverford College in Pennsylvania. However, we're claiming her as one of our own because she went there from Portsmouth University, where she had been for many years. Her main research interest is in extragalactic astrophysics. She's also a project scientist at Galaxies Zoo, which some of you may have heard of, and actually at least one of our listeners is a big part of. Hello, Alice. Amongst other things, Karen has contributed to a book on women scientists, to BBC Ideas, and also to the 30-second series of books. Her most recent one is The 30-Second Universe. There will be links to that in the chat. And she also has 30-second space travel in development. So Karen's going to talk to us for about 45 minutes. We'll then have a break for you to refresh your drinks before our Q&A. Please donate generously. And over to you, Professor Masters. Thank you very much.
Thank you very much. It's just checking that I'm good. Well, hopefully I'm good. Yes, not too much feedback here. It's a pleasure for me to join you today, this evening for you, for most of you, I believe, here in Pennsylvania. I'm very near to Philadelphia. It's the afternoon, and the groundspeople just outside have chosen this moment to mow the lawn. So if you hear some buzzing, that's what you can hear. But as Cleo said, let's try to put aside some more down-to-earth concerns. It's a tough thing at times, but hopefully I can provide some much-needed escapism this morning. This evening. And the book, the 30-second book that we've written, and I've got my copy of it right here, is actually set up, I think, for the age of distraction. It aims to cover all of cosmology in short articles. They're not supposed to be overly technical. It's aimed at a popular audience. It's not a textbook, but it's a sort of dip-in book type style. It was great fun to work on this book. It was a collaborative book, and so here I have some pictures of my co-authors, and that's the front cover of the book also. Charles Liu, who you see there, is a professor at the City University of New York, Staten Island, and also affiliated with the American Museum of Natural History, so the picture of him in front of the Rose Dome there. He kind of put this together. He put together the team, so he invited me to participate in this along with Professor Seville Salour, who is a particle physicist who works at Rutgers University in New Jersey. Depending how good your American geography is, New York, New Jersey, and Philadelphia are all very close to each other. And so last summer, we actually got all of our families together to celebrate the release of this book. And so that picture, you can see us there celebrating the release of the book. Second, I don't know if you've heard of this book series, but this is a series of books from the Quarto group publishers, Quarto knows. So here are just a selection of them: 30-Second Universe, 30-Second Feminism, 30-Second Medicine, a variety of different books. They're commissioned books, so the editors find people who they want to write on these topics, and we're paid a fee to do the writing, and then all of the profits from the book go to the publisher. So that's how that works. As someone relatively new to publishing, this was a new concept to me, but it was interesting to be involved. So the way we set up the book, it's this sort of 7-step path to understanding the universe. So the articles in the book come in 7 different categories that are listed here: the origin of the universe, the observable universe, the quantum universe, the physical universe, the metaphysical universe, the fate of the universe, and the multiverse. Now, this was a collaborative book, and Charles, as the lead author, set up those 7 topics, and we sort of divided the articles between us. As it happens, my interests really are in extragalactic astrophysics and sort of the evidence and the observable cosmology, observational cosmology. So how we understand or how we know what we know about the universe is much more my interest. So I actually only contributed articles to the origins of the universe, the observable universe, physical universe, and the fate of the universe. I'm going to leave the more speculative quantum universe, metaphysical universe, and multiverse topics out of this talk and focus more on the topics that I contributed to in the book that tell a story about how we know what we know about the origin and the fate of the universe. Now, alongside the sort of topical articles in the book, we also did lots and lots of biographies talking about how science is done, the people who do science. Each article comes with a very short 3-second biography. Each sections also has a longer biography. And I had the pleasure of writing 3 of those biographies for Hypatia, Henrietta Swan-Leavitt, and Vera Rubin. Cleo mentioned I'd previously written a chapter in an anthology of stories about women in science. That was on Mary Somerville, who's another interesting woman in the history of cosmology and astronomy. And it was a pleasure to write more about these 3 women as well. Henrietta Swan-Leavitt and Vera Rubin will come up during the story. Hypatia is a little bit before the topics I'm talking about, really. She was a very early astronomer, the first woman to have been recorded as having been an astronomer, and did some very interesting things in ancient Alexandria, but I won't talk more about her here. You'll have to read the book or read about her elsewhere. One really fun thing about working on this book were the graphics. So each of the articles is accompanied with a really vivid and sort of realistic montage of real data, in some cases real images, sometimes some of the theories. These are all done by this graphic designer named Steve Rawlings, who actually I've never met, but I went to his website and he has these really interesting sort of collage type graphic designs. Here are some examples of that. And you're going to see some of the artwork that he did for the book throughout this talk as I illustrate the topics with the artwork from the book. So even with this structure and these short articles, it's a big ask to sort of summarize the 14 billion years of history and all of the topics that go into our understanding about what happens in the history of the universe into 30-second chunks. So I'll do my best, but we are going to be giving things quite a light touch. So I will encourage you to obviously go look at the book, but also, if different topics strike your interest, you could probably do an entire talk on any one of the topics that I talk about. And I hope by the end of the talk, you will at least be familiar with the things that are shown on this slide. So I'm showing an example of a galaxy. I'm going to talk about those, close to my research heart. The contents of the universe here, which we'll cover. And this diagram, which is a NASA visualization, which I have annotated with a telescope that I use all the time, is supposed to show the history of the entire history of the universe. And we will discuss a number of these epochs and significant events in the history as we go along. So as I mentioned, galaxies are my sort of main love in terms of my research. I would call myself an extragalactic astrophysicist. Galaxies really are the building blocks of the universe. This is an image of my favorite galaxy, the Whirlpool Galaxy, which is up in the Big Dipper, near the Big Dipper, the Plough, that constellation or asterism. So it's an interesting object in the northern sky. And here you have the visualization done by Steve Rawlings that accompanies the chapter on galaxies in the book. So galaxies, the majority of things in the universe are in galaxies, and galaxies are the way we observe the universe for the most part. These are the sort of fairy lights, if you like, on the branches of the Christmas tree that kind of, in the darkness of the universe, light up the structures that are out there in the universe. So in order to understand the universe, we have to understand galaxies, and that's what a lot of my own research has to do with. There's a lot of galaxies out there. So this is a set of 255 galaxies from the Sloan Digital Sky Survey. So the SDSS will come up a few times in this talk. It was a really important survey in the history of cosmology, in the history of observational cosmology. This is the telescope that we use, or one of the two telescopes we use now. It's a Apache Point Observatory in New Mexico. It had been closed down for COVID until 2 nights ago, I believe. We're just starting observing again because the New Mexico is coming out of some of the lockdown and stay-home orders. So we're still observing with the Sloan Digital Sky Survey. We still take spectra almost every night. But it has had a number of sort of finished surveys, and it has a 20-year history of surveying the universe. And one of the most famous surveys is the 1 Million Galaxies survey, which was released by SDSS in 2008. And so these 225 galaxies that you see are some of those 1 million galaxies. And this is, a big data type moment in astronomy, right? We're starting to get into the millions in our catalogs. And it was the size of the data set from SDSS which inspired Galaxy Zoo, which Cleo mentioned in the intro. And this is something I've worked on for the last 10 or more years now. I'm the project scientist for Galaxy Zoo. And we still meet, the science team meets every 2 weeks to discuss the papers we're working on. We still have galaxies on the site, so we still invite you to go to galaxyzoo.org and help us classify galaxies. We have classified all of the Sloan galaxies now, but there are other surveys that are coming or are done. So there's one called Decals, which is currently live. And Galaxy Zoo is also now part of this larger Zooniverse of projects. So if classifying galaxies isn't the way you'd be interested in becoming a citizen scientist on the internet, if you go to galaxyzoo.org, you can find links to the Zooniverse and find hundreds of other projects that use this technique of inviting people to classify objects or draw on objects or transcribe handwritten material, or all kinds of things that are best done by humans, better done by humans than by computers. So zooming back into galaxies, what's inside them? Well, the reason we can see them is that they have lots of stars in them. So the Milky Way, for example, the galaxy we live in, has 200 billion stars in it. So I wrote the article on stars in the book, and that was very interesting because I was teaching intro astrophysics at the time here at Haverford. And so, stars are very interesting objects. They're spherical, giant, hot balls of plasma, of gas with nuclear fusion going on in their cores. We see them as points of light in the night sky because they are so far away. But they're actually, many of them are bigger even than the sun, and just a handful are smaller. I apologize if you can hear the lawnmower. The two mini bios that accompanied the stars article were kind of close to my heart. They were Annie Jump Cannon and Cecilia Payne-Gaboshkin, two women who worked on understanding of the physics of stars. And one of my favorite t-shirts is, I have this t-shirt which has the Lego versions of, now let's see if I get this right, Annie Jump Cannon here. Annie Jump Cannon with the classification. So she was the person who classified different types of stars. the first time. This is Cecilia Payne-Gaposchkin, who supposedly wrote the best ever PhD thesis in astrophysics, in which she speculated, or she not speculated, she revealed what she understood stars to be made of, mostly hydrogen and helium. And this is Henrietta Leavitt, who I mentioned earlier on, and we'll come back to her. So galaxies have lots of stars in them. They also have material that's between the stars that we call the interstellar medium. And this is mostly different types of gases. But because most of the universe is hydrogen, most of the interstellar medium is hydrogen. And so I wanted to just mention a little bit about some of the interesting things hydrogen does. So here's a little cartoon diagram of a hydrogen atom. And so a hydrogen atom is made up of a proton and electron. And if they are aligned, they have one energy state. And if they are anti-aligned, they have a different energy state. This is a sort of quantum mechanics property that we call spin. And we know this is real because we can detect the energy change. It's a very small change in energy, but it is a change in energy. And that energy creates some light. It creates some light that has a very long wavelength, actually 21 centimeters, which is a radio wave. So there's all these hydrogen atoms out there in the universe creating these radio waves when their electron spin flips relative to the proton, and we can go and detect them. And so the image that you see there of the telescope, Green Bank Telescope, West Virginia, is a telescope I routinely use to detect this transition from hydrogen in galaxies. And there I am in the picture with one of my former students standing near the receiver that we use to detect that. That's right up at the top of the sort of arm here of the telescope, right up on this platform. Obviously, the telescope was horizontal when we were standing on it, not tipped like it is in this image. And there's lots of other things in the interstellar medium as well. So hydrogen can be in different states. It can be in molecules. It can be ionized. And some of the most beautiful, I think, astronomy images that we have are of nebula and gas clouds in different ionization states. And different atoms of different materials also create these emission lines. They create these very specific frequencies, and that will be very useful, as we'll see later. It's useful because we can figure out what they are, so we can use them like a barcode. But also the very precise wavelengths mean that we can tell something about the motions of the atoms that are emitting the light. So this becomes incredibly useful for us to understand the universe that we live in. So the galaxies, they have stars in them, and they have material between the stars. We also now know that they have dark matter in them. And so here is the illustration that was used in the book to illustrate the article on matter, bright and dark. We know that 84 or 85% of the clumpy material in the universe, the gravitating material, the material that makes galaxies, makes clumps of galaxies, is something that we call dark matter. Now, it's actually a little bit of a misnomer to call it dark matter. I think we should maybe be calling it transparent matter. It's stuff that we just can't tell that it's there. It's completely invisible. It's completely see-through. It doesn't interact with light in any way. And it only interacts with other material, with the normal material in the universe, through its gravitational effects. The jelly bean jar here is a cute little visualization of just how much dark matter there is in the universe. So the colorful jelly beans in that jar are supposed to represent the normal matter, and the black jelly beans are the dark matter. And you can just kind of visually see how much of the material that has mass, that has gravity in our universe, is this dark matter. So that's one part of the pie chart explained what this dark matter is. Well, not really, right? We haven't said what it is, but that's of course because we don't know what it is. And there's a lot of effort that goes into trying to work out what it is. And it turns out the details of what it is can impact the structure in the universe. So we talked about galaxies, but galaxies clump and they form clusters and superclusters. And so the top of this visualization here is supposed to show that cosmic web of structure in the universe. These bumps and speckles here are a similar thing, but in the very early universe. And here we have one such sort of cluster of galaxies that has been mapped out with its gravity to show that it's got most of its mass is offset from where most of the gas is, where the stuff that is creating these emission lines is. So you have all this dark matter out there in the universe, and the details of what the dark matter particles are affect the structure formation in very subtle ways. But there's a lot of people trying to work out those details. The first place that we knew Yes, right. So the first place that we knew dark matter existed for sure was in galaxies. And just to understand why we're so sure that it's there, we want to kind of step back a bit and talk about gravity. And so this is actually one of my favorite visualizations or favorite graphics in the book. Here we have Newton at the top with apples falling down on the Earth, and you've got the Earth in this sort of space-time, which was a dip in it. Now, of course, Newton was before space-time, so that's a bit of a fanciful addition. The conceptual that Newton made, and a lot of people have been talking about how he made it while he was on a stay-home order at his country estate in England because of the plague, so he wasn't able to be at his university. But he made this conceptual leap that the force that was causing apples to fall to the ground off trees and the gravitational force that causes us to be able to walk around, everything that we drop to fall downwards, what Newton wondered is could that be the same force that was holding the planets in orbit around the sun? And he worked out that it would indeed work if that force were this inverse square law type forces. So here we have two objects with mass, and this is the kind of thing we teach in intro physics classes. If they're a distance r apart, then the gravitational force between them is you multiply their masses and you divide it by the distance squared. So we call it an inverse squared law. You go 2 times further away, the gravitational force drops by 4 times. Now that type of force works incredibly well to describe the motions of the planets around the sun and the motion of objects falling on Earth. It's only when you get to very, very high gravitational forces or so very near the sun or around much more massive objects than the sun do we start to need to worry about the fact that it doesn't quite precisely work and we need Einstein's gravity, so there's a hint at that here in the space-time being shown under the Earth. But for a lot of what we do in astronomy and a lot of what we do to understand cosmology, actually, we use Newton's gravity. And one place that we use that is in measuring the mass in galaxies. So this is where Vera Rubin, who's one of the biographies that I wrote in the book, enters the story. So here we have an image of the Andromeda Galaxy, actually, and it has stars in it and it has material in it. And we can estimate from just counting how much light there is, how much mass there is in this galaxy. And then we can use what we know about gravity to predict what the gravitational force is. And so how fast a star can be moving around this galaxy without flying off. Right? If there's not enough force to hold the star in its orbit around the galaxy, it's going to fly off into intergalactic space. That's what this red line here shows. This shows the prediction of how fast stars could be moving in the Andromeda Galaxy if the only material in that galaxy is what we see in the stars. And you can see that prediction goes up as the amount of material in the center of the galaxy increases, or the amount of material is increasing as we're going out, and then it starts to drop down as we go past the edge of the visible galaxy. And we start to see the same sort of behavior as you see in the solar system. More distant planets orbit more slowly. Here you are in the center, you kind of agree with the prediction, but it's not too far out when you start to have stars and gas moving far too fast in this galaxy for it to be held together by the material we can see. And it's the difference between this calculated line and the measured line that we call dark matter. Initially it was called the missing mass, right? There is mass missing in this galaxy. There must be additional mass there over what we can see. Otherwise, the whole thing would just fly apart because of these motions that we measure. So Vera Rubin was the first person to provide evidence for dark matter in galaxies. Sadly, she passed away before she was awarded the Nobel Prize for this work, which is a shame in my view, but that's what happened. You might be wondering how we measure these motions of stars. We can't see them moving. You don't see a galaxy changing. You just get a kind of an instantaneous view of it. So how do we actually measure these motions? Well, we use a piece of physics called the Doppler effect to do this. And so this again comes back to the fact that particular elements in the universe make these very, very precise emission lines, so very, very precise colors. So you will have experienced the Doppler effect if you watch Formula One Grand Prix. This is something my family was very fond of when I was a child. So my Sundays are always full with the sound of motor cars racing past cameras, which is full of the Doppler effect. Another place you'll hear it is if you hear an ambulance go past you on the street. When the ambulance is moving towards you, the pitch of its siren will be higher than when it's moving away from you. So the next time you listen to that on the street, you'll hear the pitch of the siren change. This Doppler effect happens to all waves, so that's an example in sound. It also happens to light from galaxies. So here I have an illustration of that. So say you have a galaxy that is creating an emission line that is, or there's something in the galaxy creating this emission line that's at rest with respect to you on the Earth. You will get the sort of laboratory measurement. You'll get the wavelength that we know, we can predict from quantum mechanics that those atoms should create. If the galaxy is moving away from you, the wavelength or the color that line comes out will be very slightly redshifted, very slightly moved to the red. And if it's moving towards you, it will be very slightly blue shifted. So this is an example of galaxies as a whole, and a big surprise for cosmologists. And Vesto Slipher here noticed this in 1914 when he first measured a bunch of spectrum of galaxies. They are almost all redshifted, which is weird, unless you understand you live in an expanding universe. So you can do it for the galaxy as a whole, but you can also do it for material in the galaxy. So we can see that galaxies are rotating, and we can measure the mass that must be inside them to hold them together. So that's how we go back. That's how these measurements are made, using this Doppler effect in order to measure how much dark matter there is in galaxies. So moving on, in order to understand Vesto Slipher's observation that all galaxies are moving away from us, we need to ask the question, how far away are galaxies? And this is a big problem for astronomy. This is possibly the biggest problem for extragalactic astronomers, is knowing the distance to your galaxies. We can't go and visit them, they're too far away. And so we need to use something in them to tell us how far away they are. And we have two techniques that we use. We use either a so-called standard candle or a standard ruler, illustrated here. So the idea behind a standard candle is that if you have something of known brightness, you can use how bright it appears to be from your location to measure how far away it is. We know that when you move something twice as far away, it drops, its brightness will go down by a factor of 4. It's another inverse square law. And the same with the standard ruler. If you have something of a known length in a galaxy, you can figure out a known length scale. You can measure how far away that length is by how big it appears. It's the principle that is used in some types of triangulation on Earth. So we have to figure out either one of these standard candles or a standard ruler. And actually, astronomers have been working on this for a long time. We have figured out a number of different ways of doing this. And so there are entire branches of astronomy which are focused on comparing measurements of the distances to galaxies from different methods, right? We can constantly comparing these different methods. I'm going to tell you about just one of these methods, and that's because it was the one developed by Henrietta Leavitt, who, again, was one of the biographies I wrote. The method she developed is now known as the Leavitt law, and it uses a type of star known as a Cepheid variable star. So these are stars that vary in brightness. They get brighter and dimmer over a period of days to months. So it turns out that there's actually Delta Cepheus, so it's the 5th brightest star in the Cephus constellation, which is quite near the pole star, is the prototype Cepheid variable. Not really a surprise. It's named after the constellation, right? And it varies with a period of about 5 days. And so this is the observatory that you see in the picture here. This is where I normally would be working if we're not shut down because of a pandemic. This is the Strawbridge Observatory on the Haverford campus. We have 2 telescopes. We have a 16-inch and a 12-inch in the 2 domes. And my office is normally right below this smaller dome. And we have a lab where we ask people to go and observe Delta Cepheus and measure the Cepheid variable variability. We are somewhat hampered by this tree, which is just to the north of the observatory and just covers the patch of sky where Delta Cepheus is, which is a shame, but that's life when you live on an arboretum. So the Haverford campus is a beautiful arboretum, so we love our trees. The fact that Delta Cepheus varies with a period of 5 days tells me it's one of the fainter Cepheid variables. So the important thing that Henrietta Leavitt noticed was that fainter Cepheids vary faster than brighter ones. And actually, the period of the variation could be used to tell you how bright the star is. So that means if you can find a Cepheid variable star in a galaxy, you measure the period of its variation, and then you know how bright it should be. You know how bright it is. So by measuring how bright it appears to be in that galaxy, you get a distance to that galaxy. So this is just one of the ways we measure distances to galaxies. It was one of the earliest ones to have been thought of. And it's also important because it was the method that was used to put galaxies on this plot. So this is Edwin Hubble's plot. He used the Leavitt law to measure distances to galaxies, and he has plotted the distances in his diagram in an astronomer's unit called a parsec, which is a large unit of distance. And then on the y-axis of his plot, he is plotting the recessional velocity of these galaxies, how fast they appear to be moving away from us. Astronomers always like to point out that he made a mistake. He didn't put kilometers per second, he just put kilometers. So he made an error in his units on his graph, but it should say kilometers per second. And what this graph showed is that the further away a galaxy is, the faster it appears to be moving away from us. So not only do we have almost all galaxies in the universe moving away from us, but the further away they are, the faster they are moving away from us. And the way that we interpret that observation is that it has to be that it's the whole universe is expanding. So I just have my expanding diagram to try to illustrate that. If you imagine that you have little stickers on the surface of a balloon and you blow up that balloon, you can actually do this experiment yourself. The distance between any two galaxies will grow. And if the galaxies are further away, the amount the distance grows will be larger. So the further away galaxies are in the universe, because the motion, it's not a real motion through space, it's a motion that's driven by the expansion of space itself. The further away a galaxy is, the faster it should appear to be moving away from us because of this expansion of space. So this was a huge moment for cosmologists, just understanding that we live in an expanding universe and we can see that expansion happening because we can see galaxies moving away from us. And I would quite often ask, how it is we're at the center of this, and we're not at the center of this at all. If we figured out how to move to the Andromeda Galaxy, the observations would be the same. If you figured out how to move to a galaxy halfway across the observable universe, the observations would be the same. Any galaxy would see every other galaxy appearing to move away from it. And you can convince yourself that works in this two-dimensional analogy. If you blow up the balloon, pick any of your dots as the center and you will see this behavior. So we live in an expanding universe, and this then led cosmologists to think about what happens if you run the clock backwards. If we're living in a universe that's expanding, there must have been a time in the past where everything was very, very close together. This was called the Big Bang. This idea was called the Big Bang. I didn't write this article, as I note here on this slide, but I still know about it. And, it's an event that happens 14 billion years ago. I'm quite often asked where the Big Bang happened. And the confusing thing about the Big Bang is that it happened absolutely everywhere. It was the point in time where the distance between any 2 points in the universe was 0. So everywhere in the universe was inside the Big Bang. It was a point in time, not a point in space. It is everywhere in space. So this is the beginning of the universe. And, you might be a bit skeptical about this kind of huge conceptual leap just based on observations that all the galaxies are moving away from us. And indeed, cosmologists and astronomers would support that skepticism and try to think about, okay, what else does this predict? Well, one of the things it predicts is that the early universe should be very, very hot. Because when we move everything close together, the motions of particles get hotter. All of the wavelengths of all of the light get squished as well. And so you just basically have more energy. The early universe is very hot, very dense place. Hot, dense things glow. You're familiar with this, actually. The name we give for seeing this in the universe is the cosmic microwave background, and we'll get back to why that is. But it is literally the hot glow of the early universe. Now, I imagine you've seen, at least on TV, iron glowing hot. And you might be familiar with the fact that red hot is slightly cooler than white hot. This glow that that hot iron has, or the glow of the embers of your fire, is a type of black body radiation. That's a technical term that we have in physics for this type of radiation. It is the radiation that is, or the light which is created by the temperature of an object. Every one of us makes this. So humans create black body radiation because the temperature that we're at is what it is. The peak, or most of the radiation we make, is in the infrared. So that's why people can be detected on thermal cameras, right? Those are infrared cameras. Now, the very early universe was very, very hot, and so actually made a black body spectrum, which had its peak in the X-rays. But that spectrum has been expanded with the expansion of the universe, and we now detect it with its peak in the microwave part of the spectrum, so beyond infrared, so even cooler than infrared. It is the same, it has an effective temperature of 3 degrees Kelvin, which is incredibly cool, just because it's expanded so much from the early universe. And we detect this. We've been detecting it for years now. This beautiful visualization here shows some of the very important experiments in the history of detection. So this top one here was the very, very first radio antenna, which was used to detect this initially. They actually detected it before they knew what it was. There was this glow, sort of white noise coming from every direction. The people who were running this experiment thought it might be pigeon droppings, thought it might be all kinds of things. So they climbed up in here and they cleaned it out, and they just couldn't make this glow go away. And eventually it was realized that it was this cosmic microwave background, and they were awarded the Nobel Prize for that discovery, along with one of the theorists who explained what it was. It's much easier to detect this if you can go in space. And if we go in space, we can actually detect that it's not precisely the same in all directions. And so these are 3 space satellites. The most recent one was the Planck satellite that have been used to make measurements of this cosmic microwave background, which supports the Big Bang model of the universe. And the background image here is one of the most recent images of the entire sky. So this is like a map of the Earth, is the entire globe put on a flat plane. This is a map of the sky, the entire sort of inverted sphere put onto a flat map. And these speckles just show very, very tiny temperature variations. It's actually very precisely at 3 degrees Kelvin. They're 1 part in 100,000 variations, so very, very smooth indeed. But the tiny speckles we can detect are the seeds of structure formation in our universe. So all of the clusters and superclusters of galaxies that we see were seeded by these little fluctuations in the early universe, which we'll come back to. Okay, so back to Hubble's law. I just want to have a little segue into the Hubble constant. So Edwin Hubble discovered that there's this relationship between the distance and the recessional velocity of galaxies. And this is, you probably all at some point in school, or maybe more recently, fit a straight line to some points, right? This line has a gradient, and that gradient is something we call the Hubble constant. If it's steeper, it measures effectively how quickly the universe is expanding. So if that line is steeper, the universe is expanding more quickly, and if it's shallower, more slowly. The graph here with a picture of my former postdoc supervisor, John Hooker, who sadly passed away in 2010. This is a graph that he had posted on his door, and I think he enjoyed it as a sort of story in the psychology of science a little bit. So these are published measurements of the Hubble constant, of the gradient of this line, since 1920. And you can see Edwin Hubble got the number very, very, very much larger than the numbers that we measure today. And this is all down to uncertainty and problems with the measurements of the distances of the galaxies. So as scientists come up with different measures of distance, or refine the calibration, so refine our understanding of the distance measures, we kind of eventually come down into agreement. And by about 2000, by 2010, there was sort of general agreement of the value of the Hubble constant in these funny units. It's about 70 kilometers per second per megaparsec. So that's interesting. The reason I bring this up is that we're starting to disagree with each other again. So this is a much more recent plot. This is after John, so it's not a plot he made. I think it's published in Nature. And you can see, I've zoomed this right in. So this is a Hubble constant in kilometers per second per megaparsec, but now zoomed right in so that we're sort of roughly agreeing on numbers around 70 in the early part of the 2000s. But people are now starting to disagree. And these different colors here show different methods of measuring this. So we have the Cepheids method, which I explained to you, Cepheid variables. Tip of the red giant branch, this TRGB, is another method for getting distances. And actually, we can use those speckles in the CMB itself as a standard ruler and measure the Hubble constant. And the CMB measurements of the Hubble constant are much lower again. And so, you know, early on in this graph, in the sort of 2000 to 2008, everyone agreed it was all fine. But as people have become more confident in their measurements and dropped their errors, we start to see this disagreement. Yep. Okay. Never mind what the Hubble constant is, just the concept that this recessional velocity can be used as a proxy for distance, so it correlates with distance, means you can use it to map the universe. You don't need to measure a distance, you just need to measure a redshift. And you can do this with just a simple spectra, and it's much quicker. And so we started doing this in the late 1980s. This is, again, John Hooker and his collaborator, Margaret Geller. This is an image of the sky where each dot is a galaxy that John and his team had painstakingly measured spectra for. And if we move on, this is now going to be a little video showing that slice across the sky and showing it rotating as we have distances to all of these galaxies. And so you can see this kind of map of the universe, which I think is sometimes a little hard to get your head around. We're here at the center and we put distance along the edge, and then this is like a sweep across the whole sky. And this particular one, this CFA slice, or the CFA stickman, is famous because it showed this sort of stickman, this large-scale structure in galaxies, which was the first measurement of large-scale structure in galaxies. But there's a lot of galaxies in the universe. And so John and his team were doing one spectra at a time. We can introduce the digital revolution. So Sloan Digital Sky Survey comes back again. This is the telescope that I showed you before in Apache Point, New Mexico. And this is showing the technique that we have where we put fiber optics into plug plates and are able to measure 1,000 spectra at once. So you can imagine the speed up in terms of mapping the universe you get from going one spectra at a time to 1,000 spectra at a time. To measure these redshifts. And so this is what the original Sloan survey did, and that we're continuing to do today, measure redshifts of galaxies. And here we have a much bigger one of these diagrams where, again, we're here at the center. This is distance going away, and this is a sweep across the sky. In this example, that looks like a butterfly in two directions on the sky, both two sides of the Milky Way, actually. And you can see the kind of fluff, the so-called cosmic web that we measure. And why is this important? I just want to kind of get to why this is important, and then I'll end for questions. I mentioned that these speckles you see in the CMB are the seeds of structure formation. And so gravity brings these speckles, these very tiny speckles, and gravity over 14 billion years turns them into this large-scale structure. So we're kind of probing the same thing when we see these speckles and we see this large-scale structure. So one of the most fun or challenging articles I wrote for the book, actually, was this one on Baryon acoustic oscillations. And John appears again because he was the bio in this article. I hate this term, Baryon acoustic oscillations. I'm not a fan of using fancy words when simpler ones will work. That is the technical term we use, Baryon acoustic oscillations. What we mean, though, is sound waves in normal matter. In the early universe was a plasma, and so sound waves were propagating through the material. And this is an image of a pebble dropping into a pond. It's not a sound wave, but it has similar properties. If you drop a pebble into a pond, you'll get these rings expanding outwards, and that's what you'll get in the sound wave. Now, if you can imagine dropping a pebble into a pond that's getting colder very quickly, you might imagine that those rings freeze into place. And so that's kind of what happened in the early universe. There were sound waves and the universe was expanding. And at some point, the sound waves froze out. And so there was a particular scale that was set into the early universe based on how big those sound waves had got at that point. Now, that would be very simple to measure if it was just one sound wave, right? If it's just one pebble dropped into the pond, very easy to measure that scale. Now you have to imagine that there's just hundreds and thousands of overlapping sound waves, and this makes this incredibly complicated pattern. But if you measure very precisely the statistics, you can still get that scale. And that's important because we measure that scale. We have measured that scale using the Sloan Digital Sky Survey data. It's important because it shows that we understand the physics, but also it provides one of these standard rulers. So we can use it to measure the expansion rate of the universe. And we can actually do the same thing with the CMB in the very early universe, and then with the map of the galaxy much more recently. So this is the most technical plot I have here. This shows the expansion rate. This is the Hubble constant, effectively, but now not just now, showing it over the history of the universe. Because light has a finite speed, in astronomy, when we look very far away, we can look back in time. And so we're able to look at earlier universes. The Planck prediction here is what we think this should look like based on measurements of the cosmic microwave background. That's that black line. And all of the colourful dots are actual measurements of them. Now, you might have heard about the accelerated expansion of the universe. And what we mean by that is that this line comes back up again. And it has to come back up again. You can see not just from the Planck prediction, but because our actual measurements of the expansion rate of the universe go up and down. Okay, so back to the slide I started with, or almost the slide I started with. This, the shape of this trumpet is supposed to be indicating this accelerated expansion of the universe. And, you know, I could pretend I could explain what's causing that. We don't actually know. And we name what we don't know dark energy. We know that dark energy is 3 times as much energy density as the gravitating matter in the universe. So when we sort of count up the total energy density of the universe, 75% of it is this dark energy and 25% of it is dark matter and normal matter. So we know that is true, but we don't know what it is. We don't even know what it might be, really. There's some predictions, or there's some theories that have it be a change of gravity. But it's a big puzzle for cosmology today. And so it's very, very interesting. So I think I'm going to stop at that point, and I will skip over the fate of the universe and just end with my thanks and take questions.
Thank you so much, Professor Masters. That was really, really interesting. And it's a subject I personally find very difficult. But I think I just about held on there. There were I was watching some of the chat, and there are people who know an awful lot more about this than I do. And I think there are some really interesting questions coming up in Slido. A special thank you, because I didn't tell everybody else earlier, but you had a power outage at home today. You have no power. Was it a storm?
Yeah, there was a big, as if we needed more going on in the Philadelphia area. There was a big storm in this area yesterday with lots of trees have come down. And so I looked this up a few hours ago. There were 3,000 power outages and 180,000 people without power. America has this fondness for overhead electrical wires, which I always think is a bit strange, given that we have winter storms and summer storms that knock down trees quite frequently. But yeah, as far as I know, no power at home at the moment.
Right, well, thank you again so much for braving all that and coming out and talking to us. I've got quite a few other things to say, because I think it was a little bit emotional in the introduction and forgot all sorts of stuff. So I do apologise for that. Thank you very much, everybody, for your donations. You're being super generous. You've already passed the £200 mark, so that's a few people who've going to have to stump up their full offer, and we're heading rapidly towards the 500. So thank you so much for your donations. Really, really well, very much appreciated. One thing I didn't announce at the beginning, but the moderators have been really good about putting it in the chat, is the Slido, SLI, well, it's all there. If you follow that, there are a number of questions that have been asked. Some people have been particularly active. We'd really like you to ask your questions, and if you don't want to ask a particular question, please upvote the ones that you are interested in and that you most want to hear the answer to. We'll get through as many as we possibly can. Also in Slido, there is a poll. We have a Zoom meeting after this particular talk, after all our talks, to mimic what we would normally do in the pub after a talk, which is to go and have a drink afterwards. We've decided that we need a name for our pub, so they're all there on the Slido poll. Please go and have a look. Next week's talk, we have Cara Santamaria in conversation with Marsh. Cara Santa Maria of Talk Nerdy fame, of Skeptics Guide to the Universe fame, and lots of other things. So I don't want to sort of pin her down to anyone in particular. That will be a really interesting talk. Marcia is just a brilliant interviewer, and it'll be very, very engaging. The week after that, as I said, with Angela Saidi on the worrying rise of race science. I shall steer away from that or I'll get emotional again. We're now moving into the break. During the break, please refresh your drinks. I gather there's not much of a queue at the bar. Please go into Slido, ask questions, continue the chat, and we'll be back at 8:15. See you then. Thank you. Hello everybody, welcome back. I hope you've all refreshed your glasses. I hope you've all had a look at the polls and looked at the Slido questions. First of all, talk about the polls. There are a number of suggested names for the pub. There's quite a lot of votes and the top few are neck and neck. So there's everything to play for. Head on over to Slido, go to polls and choose your favourite name for the Zoom pub. We'll let you know at the end of the Q&A who's won and then we'll go straight into Zoom. Welcome back, Karen. I'm not sure which side of you are. Do I look left or right to see you? Never mind, I'll move straight on to the questions. There are a number of really interesting questions which we've had a look at. I'm really pleased to announce that Dave the drummer's question has risen to the top, but I will read it to you. We've had a little bit of a discussion about this. What do you think about the new evidence for a potential parallel universe going backward in time that was reported in New Scientist recently? Is it a thing?
Well, everything is a thing. And I was sort of sharing before we came back live that I don't think this is a big thing. If this is something that lots of cosmologists believe, you'd be seeing lots of chatter about it, even in today's world, on Twitter, indeed. So cosmologists and astronomers are pretty active on Twitter, and that's one place where I engage. I had a quick skim of it. What it looks to be is particle physics evidence for some kinds of antiparticles that could potentially be explained by a parallel universe. I'm going to be skeptical on this and say I think we need more evidence to claim that we've definitely detected a parallel universe.
Right, thank you. I'm actually just going to interrupt the Q&A a bit, just because we've just had a report on how much we've raised so far with the donations. Everyone's been wonderfully generous. Thank you so much. We've raised £750. That's just stupendous. That's an amazing amount of money. And that means that with the match donations, we're going to be up to 2,500. It's a really worthy cause. Thank you so much, everyone.
That's wonderful. Thanks, everyone. Yeah.
And I think, given your thoughts when we spoke earlier this week, I'm sure it makes you feel better about talking about such a light.
Yeah, I was reflecting that the schedule seemed a bit wrong, that Angela Saini's talk would be very appropriate today, given the events. And I hope to actually be able to join and listen to Angela. So I'm very much a fan of her work. So.
Right, moving on to Sean Ellis, who has been very busy in Slido. The gravitational wave astronomers have recently announced that large neutron stars are likely to have quark liquid cores. How do they know?
So this again is as much like the sort of Baryon acoustic oscillations, very detailed patterns. And so the gravitational wave signal that comes from when neutron stars merge with each other or neutron stars merge with black holes has a very, you can measure the shape of it very precisely, and people model that shape, and the details of that shape can tell you about the internal structure of neutron stars. I'm actually married to an astronomer who works on neutron star gravity and internal structure of neutron stars. He's a massive skeptic of quarks in the centers of neutron stars. So I'm going to have to say that he doesn't think there's any evidence yet for quarks inside neutron stars. He thinks it's likely to be normal neutron matter, but I don't know. I mean, it'll be modeling. It's modeling of the signal that comes from the gravitational wave that they create when they merge, and it's so amazing that we can do that now. So it's really exciting.
So it's theories, really, still.
Yeah, I mean, everything's a theory at some level, right? We you make a prediction, I was teaching Astro 101 this past term. So, the scientific method, you make some kind of prediction, and then you test that prediction against evidence. And so the evidence here is the gravitational wave signal, and the predictions are the models of what neutron stars with different interior, what their signals would look like when they merge. And so someone has made a prediction for a quark interior, and that matches well with a signal, and that's where that will have come from.
Right, that's great, thanks.
Yeah.
Gerald from Cologne Skeptics in Germany asks, where can we get the female astronomer's Lego shirt?
Right, so I was trying to work this out. It's a while ago that I got it, and I was looking actually at the slide, and it says on the slide that it's from shirtoid.com. I don't know if that's the best place to get it, but shirtoid.com appear to sell it. And they also sell a similar one based on the characters in Hidden Figures. Well, characters, they're real people, right? The female black women computers at NASA, the movie came out about, which is a nice one.
I imagine your daughters will be interested in that, Gerald. Good present. Next question is from Duncan Power. Besides gravitational effects, do we have any other evidence for dark matter? If not, why do we believe it's dark matter? Oh, it's just jumped. And it's just jumped again.
People are voting.
Why do we believe that it's dark matter rather than the effects of an unknown sixth force?
Yeah, that's a great question. And again, it comes back to our ideas about models. And I think you can show the picture that I'm showing on my screen. This is one of the biggest pieces of evidence that we have that dark matter is a particle rather than a change in force. This is a picture of something called the bullet cluster, and it's actually 3 pictures that have been overlaid in different colors. So you can see the image of the galaxies, and it's going to have some foreground stars as well. So we're looking at this through our own galaxy, right? So that's a foreground star with the spikes, but you've got galaxies in the sort of orangey color. Excuse me. Then you have in the red is hot gas. So hot gas, which creates X-rays. And in the blue is where we think most of the mass is based on gravitational lensing, actually. So it is still a gravitational technique, but the bending of light. And what's happened here is that these two galaxy clusters have collided with each other. The dark matter doesn't interact at all except gravitationally. So those two big blue blobs have kind of passed through each other more quickly than the gas, which has kind of has some shocks. You can kind of see the shape of the shock, and it's sort of got some drag forces and is now dragging behind where the dark matter is. And so this shows that dark matter and the gas in the clusters have kind of offset from each other. So you can't do that if it's a force. You can only do that if it's a particle. You can't separate the gravity from the stuff if it's a force. You can only separate the extra gravity from the visible stuff if the extra gravity is caused by a particle. And so this is taken as really strong evidence that dark matter is a particle, not a changed force, but people are continuing to investigate so-called MOND theories that could explain some of what we see in galaxies, and people will continue to do that, I think, for a long time still, but most astronomers are very confident that dark matter is some kind of particle.
Thanks.
Oh, so if you stop sharing that now, that would be good.
Oh, that was nice, actually.
I keep. Yep.
So Sean Ellis is asking another question. And IIRC, who are IIRC? Oh, right. Yeah, because Sean, it's me reading these questions. So if I remember correctly, I've seen galaxy collisions where the galaxies collided, but the dark matter continued.
Yes.
Are the dark matter-free galaxies spinning themselves apart?
So I think that was actually someone remembering the bullet cluster. So this is the image I just showed, and so it's a galaxy cluster, not a galaxy. And so where you see that the material, the dark matter has continued and left behind most of the material. Yes, that cluster is not in gravitational equilibrium, to use a technical term. So it would not be yes, it might be kind of falling apart and moving, like exciting things are happening. It's merging. We do also find some galaxies that have very little evidence for dark matter. And ironically, that's yet another piece of evidence that dark matter is a particle, because if you can find galaxies that do not have dark matter in them, it must be a thing that you can remove from galaxies. And so there's some very low luminosity, very, very small galaxies where the motions of the stars appear to not need much in the way of dark matter to explain the galaxy being held together.
Right. The next person is anonymous, but they're particularly interested. I think they wanted to hear the rest of your talk because they say, "Oh, what were you going to say about the fate of the universe?"
Yes. Well, I'm quite happy. I'll do the sort of quick version of the last few slides of my talk. And I can also report that I just got a message that power turned on in my house. So I'm very happy about that. Anyway, so if we can go back to screen sharing, I can just show very quickly some of the slides. And actually, this was some of the most beautiful, I thought, illustrations in the book. Typically not articles I wrote myself, which is why I kind of focused on other parts of the book. But some beautiful illustrations of what's going to happen in the sort of the future history of the Earth. It's not very cheerful for the most part, but it is a very long time away. So I wanted to point out that in humanity, recorded history is about 5,000 years long, and it's been about 100 million years since the dinosaurs roamed the Earth. So 1 billion years, which is about the amount of time we have left before the oceans boil, is 200,000 times the span of human history. So we have 200,000 chances again before the oceans boil, because what's going to happen is the sun is a star, and stars do run out of fuel, and eventually the sun is going to be very gradually expanding and getting hotter, and in about 1 billion years will be hot enough to boil off the oceans of the Earth. So you can see sort of some of that visualization here. And in about 5 billion years, so a long, long time in the future, the Earth will most likely be swallowed by the expanding sun. So this is all a very long time in the future, but all not great news. So some more visualizations here. You can see the sun expanding, and it will swallow the inner planets, Mercury, Venus, and possibly Mars. And we're not quite sure. As the sun expands, gravity will change a bit, so the orbits of some of the planets might change. So Mars may or may not get swallowed, but Mercury, Venus, and Earth will.
We need the TARDIS, really, don't we, so we can watch it?
We need to get on with interstellar travel if we're going to be around. But we've got 200,000 times the span of human history to figure it out, right? So that's a long time. So hopefully we can figure out interstellar travel as a species on that timescale. This is a beautiful illustration as well. This is showing the life cycle kind of the sun. So you've got the normal sun now expanding as a red dwarf, kind of expanding more, and then eventually turning into a white dwarf. And this sort of hint at the planetary nebula, which is the sort of the outer layers of the sun, will get puffed off into space. Very, very beautiful. So as well as the sun expanding to swallow the Earth, at about the same time scale, the nearest galaxy to us will start colliding with the Milky Way. So galaxies collide all the time. Even though we live in an expanding universe, gravity pulls everything together. And so I kind of talk about, galaxies can move around the universe, much like you can move around on top of the moving walkway in an airport, right? The walkway kind of carries you along. The expansion of the universe is carrying things along, but stuff can move around on top of that. And that's why galaxies end up merging, a bit like sort of raindrops merging as they fall down the window pane. Some really beautiful images from space. This is an image of the night sky sort of now. It's a very dark location. I took the credit off it. I think the photographer is called Stefan Vetter. So this is the Milky Way stretching across the sky. And you can just pick out the Andromeda Galaxy here, just a little galaxy. It's the most distant thing you can see with the naked eye. I once saw it from outside the Winchester Science Centre when I was living in Portsmouth. So you can definitely see it. And here is a visualization of it getting closer to us. So you can see Andromeda getting closer and closer until it starts merging with us. And eventually the two galaxies will merge. The space between stars and galaxies is so large. This is like clouds merging. Like it's very unlikely any two stars will collide. But nevertheless will be an interesting event at about the same time that the sun swallows the Earth. And then if we want to kind of go on even further, Charles, I think, wrote this article. I actually really like it. It's hard to talk about the heat death of the universe in a positive way, but Charles talks about the ultimate perfection of, the universe will be incredibly smooth and there'll be no chaos anywhere. Each horizon will contain just a single atom or subatomic particle. And this is the ultimate fate of a universe where the expansion is accelerating, right? We will keep expanding faster and faster and faster until we end up with a universe where the temperature is very close to absolute zero and each universe just contains one particle. But the time scales are ridiculous. So 10 to the 100 is bigger than a Google. But that's it's more than that years in the future. And I worked this out, it's ends up being 10 to the 97 times the span of human history. It basically doesn't matter. It's so long in the future. This will never impact anything. But it's interesting to think that this is the ultimate fate of our universe.
I'm just going to say something a little bit frivolous now. I've just found a new way of identifying astronomers and physicists, is that they round everything up to noughts.
Yes.
You said 100,000 years for the dinosaurs. That's the kind of thing Brian Cox would have said, isn't it? Millions, billions, hundreds, thousands. The rest of us have sixes and fives in that number. But now I know how to identify an astronomer. Yeah,
we don't like to be too precise. So astronomers, I'm often working with this with my students. People will be very precise. Engineers are very precise. They need to be. We need the bridges to be built precisely. But physicists and astronomers will tend to like to round numbers because there's usually that kind of uncertainty. And also, I can remember rounded numbers better. So
yes.
Especially for giving talks, I remember the rounded numbers. Brian Cox has someone feeding him numbers, I'm sure.
So millions and billions he needs feeding.
Yeah.
So Anonymous says, are there any, I really like this question, are there any big ideas from science fiction, such as warp drive, that you think might be possible one day? My favourite would be the Ansible, the instantaneous communication.
Oh, yeah, not having to worry about time delays.
Yes, funny fans there.
What is it? The Expanse we've been watching. I like how that actually portrays light travel time. So you can't talk instantaneously with people across the solar system. It's quite nice. I think one that I'd really like would be the transporter. And I think I have definitely read that people have transported very, very small things. So turn them into information and sort of beamed them across space. Wouldn't that be good? We sort of solve the problems of dual careers and commuting if you could just be transported to wherever you needed to be instantaneously. Also, it'd be I think it would be very disappointing if we are not able to travel faster than the speed of light. It'd be really nice to be able to explore the universe and go and do those things. As everything we know about in physics says that the speed of light really is the ultimate speed limit. There's really no way. You need infinite energy to reach it. Any microscopic particle that hit you would explode your spacecraft. There's all kinds of reasons why traveling so fast is not going to be possible. So it'd be really nice if we could figure out that there's a way to get around that by entering some parallel universe or something, but not as far as we know.
It was.
Yeah.
So Helen asks, you mentioned some of my astrophysics heroines. Was it a conscious choice to choose female physicists to profile in the chapters?
To some extent, yes. Obviously there are men who've done important things in the history of cosmology too, but they've actually typically had a lot of stuff written about them. So I wanted to make sure that the women whose contributions have been overlooked were not overlooked in this book.
Good. That's many of us like to hear that. There's another question that I think you might find quite interesting. It's from Anonymous again, who says, I have a friend who thinks the Earth is flat. The moon landings are fake, along with all the other unusual other theories. Where do I start with him?
So this stuff is difficult, and it's something I have an interest in, and I won't claim to be an expert, but one thing I've been reading about is the importance of yes and when talking with people who disagree with you.
Yes.
So trying not to say you're wrong immediately, but trying not to be dismissive or making fun of them. I think it's very easy for us to sort of make fun of people who believe the Earth is flat. But one of the things I really like about that group of people is the emphasis they have on testing stuff themselves, right? I think that's fantastic and very much in line with the Skeptics' philosophy. they're just kind of getting the wrong end of the stick with some of the tests. And so one thing I think would be good is okay, well, what if the Earth was flat? Let's explore that. What would happen? What are some of the consequences? And can we convince ourselves that it can't be true? I've seen stuff about how, water is always flat, but then you can find an image of a globe of water in space that's a sphere on the International Space Station. Just kind of, I think, I really feel quite strongly that we are doing these people a disservice if we just make fun of them and dismiss them and don't want to engage with them. They all desperately want to be scientists, right? They're super interested in science. So let's help them to explore their interests and hopefully help them to find out for themselves that they're wrong. There's all kinds of psychological stuff that it's going to be very difficult for the people to admit they're wrong, particularly the leaders of these organizations. It's going to be very, very hard. They've become famous, made a lot of money in some cases by being proponents of these views. It's going to be very hard for them to admit that they're wrong. And so they're probably not the right people to start with. But
some of them may even have decided that they're wrong, but be stuck, I suppose.
Yeah, well, you can kind of imagine getting stuck in that kind of problem, right? It's very interesting. I recently watched there's a movie, a Netflix movie about flat Earth societies that I recently watched. It's very interesting. And if you're interested in this, I think it will give you some things to think about. But yes, I think trying to bring people along and trying to work with them where they are.
There's one I like here. I completely understand the question. I think that's why I like it. Left field, unimportant logistics question. The SDSS is open when working. How does the mirror stay free of dust, bugs, and bird byproducts?
Very nice. Well, it gets cleaned once a year, is one thing, so it doesn't entirely. There is a building that rolls over it. So the images you've seen, it looks like it's just, a telescope that's out in the open, because obviously those are the best pictures. But you can find on the web, we have the SDSS has a YouTube channel, and you can find a video of a night of observing, and you can see the building rolling off the telescope. And so during the day, on nights when it's wet or when it can't be open, it's safely enclosed. And then you're right, when it's open, I guess stuff can happen. But it gets cleaned once a year in a special facility.
Right. That was from Sean. I'm going to follow it up with another one from Sean, which is a lot more complicated. We're looking at microwave background radiation with the entire universe in the way. Yes. How do we correct for that to an accuracy of a few parts per million?
Yeah, well, it's a very, very good question. And what we do is we look at multiple microwave frequencies. And the stuff in the foreground, the rest of the universe, has predictable spectral shapes. And so we're able to actually subtract that. And you're right, it's very, very hard to do that accurately. So you will find actually that the very accurate measurements will exclude parts of the sky where we don't believe that that's been done well. So for example, where our own galaxy is, that stripe across the sky, where the galaxy is, it's very hard to remove the microwave emissions from the galaxy and dust and stuff in the galaxy very precisely. Brian May's PhD thesis on the zodiacal light is relevant, actually. And so the zodiacal light is dust in the solar system, which creates microwave radiation, and so potentially has some impact. And so it has to be modeled, and it has to be measured at multiple frequencies to try to subtract it.
Thanks. And Alex has asked the next question. There was a news item lately claiming dark matter may not actually exist. Is that possible, or is it a minority view?
At this point, it's a minority view. There are definitely some scientists who think that it's possible dark matter doesn't exist as a thing and that it's a modification of gravity. But the majority of the community believe the evidence that we have, like the bullet cluster, like galaxies without dark matter, like the incredible match that dark matter models have with so many different parts of observational cosmology, of so many different parts of the evidence that we have. The majority of people believe that it's a particle of some kind, and there are candidates even for what the particle is. Oh, so there are ideas for what it could be. So the level of our lack of knowledge with dark matter is much less than it is with dark energy. So with dark energy, you definitely find a lot of the community talking about modifications to gravity. Maybe it's not really a thing. Like there's definitely a big part of the community talking about that, but that's a totally separate thing than dark matter. The material in galaxies, we really feel quite confident it's a particle of some kind.
Right, thanks. Rebecca says, back to the 30-second series books. Would they be suitable to read to young children? And if not to young children, what age do you think they are suitable for?
I definitely have friends actually who have 30-second books in their house, and they have children. My kids are about 10 and 13. They're not about, they are exactly 10 and 13. I think they would read this. They think that because mom does astronomy, it's not the most interesting thing. But, if you have kids who are into it, I think 10-year-old could probably read it. An interested 10-year-old, yeah, no problem.
Speaking as someone whose kids are a bit older than that, you may find that their partners are more interested than the children themselves are. Anyway, moving swiftly on from that one. Anonymous here asks, the 3 ways of calculating the Hubble constant had error bars which don't overlap. Why is this?
Well, we don't know. And so that was sort of one of the points of that slide, is that that's an interesting puzzle for observational cosmologists right now. Different methods of measuring the Hubble constant, we don't agree. So what's going on? Well, either someone, or maybe everyone, are underestimating their errors. Someone maybe has some kind of systematic error that's not counted for, so the point's going to move a lot. Or there's some physics, something going on in the universe that we don't understand yet. It's always an interesting point in sort of observations when you have these sort of non-overlapping error bars. You're trying to measure the same thing different ways. We do it all the time in cosmology and astronomy. And if they don't agree, that's the fun bit. That's the bit where we're like, oh, there's more to do. It's also nice when they agree, because then you've got it right.
So you can't just plump for one of them you like best then?
No, I'm not going to do that. I have opinions, but they're not very evidence-based, so I'll keep them to myself.
Okay. Yeah. Somebody else has been thinking about the 4 fundamental forces, gravity, electromagnetic, strong and weak nuclear, and saying, are they just conceivably knots and tears in the foremost, which is gravity?
That's interesting. It's been a puzzle for theoretical physicists for a long time to how to combine gravity with the other forces. So we talk about electromagnetism very comfortably. The electroweak force. So you can go back in the early universe. There's a period of time when electromagnetism and the weak force basically combine. The strong force goes in there as well. So those 3 forces are easy enough to combine. Gravity, we've struggled with the ability to get a quantum gravity, a theory of quantum gravity. So when you think about the singularity in the center of a black hole, or the singularity that's the Big Bang, both of those are very tiny, so we need quantum physics, and they're also, very strong gravity, or the whole universe. So we start to need general relativity. We need Einstein's theory of gravity, and no one yet has fully been able to combine those two. And so that's also interesting for us. There's more to learn. There's more to understand. We don't really know what causes gravity. We don't really understand it. So I think I'm not going to speculate if the other forces could be caused by tears in gravity, because that seems completely out of my understanding. But it's an interesting question for sure.
Right. I'm going to ask just a couple more questions, and then we'll move on to the drumroll, the pub.
Oh, the pub name, yes.
Yes. So I'll leave that one till last. Actually. What's the next one? I'm going to ask you a scientific one first, and then actually a couple of fun ones. Has anyone managed, because this is the next one in the list, has anyone managed to make an image correlating the CMB and the observed galaxy clusters?
Yeah, I mean, you have to think there's a time difference, but yeah, people definitely look. And so, the observed clusters we're looking at later than the CMB. So they're not going to be the same clump, but people definitely look at correlating the two. There's techniques that look at lensing in the CMB, so you're actually measuring the lensing signal of the foreground clusters. This is definitely something that people do. But bear in mind, it's not that clump makes this galaxy cluster, because those are at 2 different times.
Right. I'm quite excited with just how much people have engaged with your talk, actually, and they're asking really quite detailed questions. One here, are galaxies expanding along with the universe?
That's a great question. I love that question. I remember a kid asking me once, are my eyeballs getting further apart because of the expansion of the universe? It's really, really fun. You can kind of think of every little sphere in the universe as being its own little expansion area, and its expansion properties depend on the density of material inside it. So my head is very dense compared to the rest of the universe, not expanding because the gravity and actually electromagnetic forces inside my head are keeping it together. The Earth not expanding. Galaxies, the gravitational force is keeping them together, so they're not expanding. It's only on the scale of bigger than galaxy clusters that we start to see the expansion, really. And that's because you have to make these spheres, and inside that sphere there's a lot of material, and so it causes the universe to recollapse in that sphere. But then when the sphere gets big enough, it's expanding.
Right.
Hopefully I got excited about that answer. Sorry, I was just, but hopefully that was understandable.
And that's really interesting. I mean, I'd never thought about the eyeball bit, but now I will.
Not expand. You don't need to worry about it. You don't need to worry about the expansion of the universe between your eyeballs. It's not happening.
Right.
So
my head's too dense, basically.
Yes.
Right.
Yes.
And the last question has to be asked because it has a little winky at the end of it. And it reminds me of my horror when I was in Cape Town and Orion was upside down. Oh. The question is, do galaxies in the southern hemisphere sky spiral the other way?
No. So the direction, the orientation of spirals is random, which it should be, because we believe the universe is kind of isotropic and homogeneous. So there shouldn't be a preferred rotation sense. It's actually one of the things early on measured in Galaxy Zoo. Interestingly, the first measurement without a calibration from Galaxy Zoo did suggest there was a favored spin. But it turns out it was probably something to do with either the psychology of people or the site layout. People were more likely, when uncertain, to hit one of them than the other one. And so we actually had to put in galaxies that were flipped and found the same signal, even in the flipped galaxies, to just sort of calibrate out this human or possibly site design measurement. But yes, absolutely no evidence. By the way, a great way to talk to your friend who likes the flat Earth, see if they'd like to go with you to the southern hemisphere and see things upside down. Anyway.
Yeah. Okay.
It's always fun to do that. I like doing that. The moon upside down is fun.
Right.
Yeah.
Thank you. I think we'll call it a day there. We've had about half an hour of Q&A, which I think is usually feels about right. And we've also got people champing at the bit to know the answer. The donations have carried on going up. So once again, can I thank everyone ever so much for that? We're very grateful and really proud to be part of a community who can raise that much money that quickly for something important. It's actually really heartening. How much, sorry? 890, and that's without the extras it put in. 2,690 with the extras. So that is amazing, everyone. Thank you so much. And now I'm going to have to ask Kelly, who's been masterminding the Slido poll, to let us have the answer. Do you want to give me the answer or do you want to talk?
Yep, I don't mind talking.
Hand over to Kelly. Thank you.
Okay, so in joint second place, we've got the Bayesian horse and the hook, line and sinker, both at 22%. But the winner with a mighty 27%, not that mighty, is the Lockins razor. Thank you very much, everybody.
That's brilliant. Therefore, we would like to invite as many people as would like to join us at the Lock-in razor in 10 minutes, 15 minutes? 9 o'clock, yeah? So we will see those of you who'd like to at 9 o'clock for a drink in the Lock-in's razor. Once more, though, can I thank Professor Masters for a really interesting talk. As I said, it was just at the level that I had to really concentrate to understand it, but understood it, which is, as far as I'm concerned, that's spot on perfect. So thank you so much for that. And next week, we have Cara Santamaria in conversation with Marsh. So please join us again for that. And lots of clapping, cheering and whooping, please, in the chat to say thank you so much to Professor Masters again. Thank you.
Thank you very much for having me.